In this lecture session, I am going to discuss about the topic on the single-phase full-wave control rectifier with RLE load. Before introducing such type of converter circuit, let me understand what is the concept of RLE load. First, consider a loop construction of a DC motor. This one is suppose N or N pole. This is suppose S pole, and the direction of the flux, that is from N to S in this way, and we are placing a rectangular shaped copper conductor between the two magnets in this way, and the end part is connected to a DC supply through popper mechanism or slip ring. So this is actually the loop construction of DC motor, in which normally this N pole and S pole, which can be taken from the stator part or stator part or stator slot, and the rectangular shaped copper conductor, which is actually nothing but a kind of armature conductor, which represents the total armature part. And we are placing this conductor between the N and S pole, where the uniformly flux distributed area has been occurred. Now we are applying the DC supply over here, and that is suppose VDC. That means what? When we apply the DC supply to the conductor, then we can say we are placing a current carrying conductor in a uniformly flux distributed area that has been occurred due to presence of two permanent magnets, that is N and S. Then what happened? It experiences a force as per the Faraday's laws of electromagnetic induction. When we are placing any current carrying conductor in a particular magnetic field, then the conductor experiences a force. As the two sides of the conductor, one side that is close to N pole and a different one that is close to S pole, that is why the force that will be applied in the opposite direction. That means the force which is acting at this side and the force which will be acting at this side, both will be opposite in direction. That is why it produces amount of torque, and due to which then the conductor starts moving in any direction based on the Faraday's laws based on the Fleming's light hand rule. Now see, when this conductor starts moving, then two sides of the conductor starts cutting the few amount of flux as per the Faraday's laws of electromagnetic induction. As we all know, then when the conductor starts cutting the few amount of flux, then what happened? An EMF is induced on that particular conductor. And as per the Lenge's law, we know this nature of the induced EMF, that is always opposite of the original voltage source. So we assume when we applied this VDC, then the current starts flowing in this way. That means this is the current I which starts flowing to the conductor, rectangular shaped conductor. Then what happened? It experiences force, and it obviously the torque is produced. Then this armature starts moving, or this current carrying conductor, which is replaced in terms of armature, then it starts moving. Once the armature or this conductor starts moving, then the two sides of the conductor start cutting the few amount of flux as per the Faraday's law, that is true, and EMF is induced, that is always in opposite direction of the supply voltage. That is why, as per the Lenge's law, that the direction is always opposite of supply voltage. That means from this operation principle of any kind of the DC motor, we can say when the original current I starts flowing across the conductor due to presence of the resistance of the armature that is defined by RA, then the ohmic drop across the conductor that can be replaced by I into, that can be termed by, that is I into RA. Okay. On the other hand, when the back EMF is induced as per the Lenge's law, that is opposite of the original supply, which stands for actually E, opposite of original supply voltage, as well as this conductor, this rectangular shaped conductor, that is actually taken out from the armature winding. As the armature winding, that means a huge number of coils are there to form, huge number of conductors are there to form a particular coil. That means it has inductivity or defined by L. So this is the concept of R and L and E. So this is the concept of RLE load. That means RLE load nothing but a kind of application purpose, that can be DC motor also. Okay. Now I am going to demonstrate the topic and the operation principle. So let me go to the circuit diagram first. This is the pictorial representation of the two connections, that is M2 connection and B2 connection, for the case of single phase full wave control rectifier for RLE operation, in which in case of M2 connection we are using a center tap transformer whose primary winding is connected to the supply and whose secondary winding is center tapped, in which we are adding this load part, that is RLE load, and two thyristors are used, that is T1 and T2. So in this circuit, the supply current, suppose for the primary winding, that is IS, and the thyristor T1, the voltage appearing for the first thyristor, that is VT1, and the voltage appeared across the second thyristor, that is VT2, and the voltage appear across the load, that can be defined by V0. Okay, so this is all about for the M2 connection. Now in case of B2 connection, we have used, that is a 4 number of thyristors here to form a bridge circuit, in which T1, T2, T3 and T4 are used. Okay. Additionally, a transformer is there to isolate the total this converter part from the supply. That is why we are using a transformer, but in this case we are not using the center tap transformer. That means the input voltage of the primary, that should be equal to the output voltage to the secondary part, if we assume the number of turns in primary and the secondary winding both are same, and the RLE load is connected across the bridge. So this is all about for the B2 connection. To demonstrate the working principle of such kind of converter circuit, here we are going to explain the total scenario by using the B2 connection. Okay, that is why we have taken the different axes which will define the each parameter of the circuit. That is, first one is Vs. Vs means that is supply voltage, this one. Vp is the voltage, that is supply voltage to the primary winding of the transformer, and Vs, that is the output voltage of the secondary winding of the transformer, that is actually fed to the converter part. That is why this is the input supply voltage of the converter, as it is a AC supply. Okay, as is a output of the transformer secondary winding. Next is, that is the gate signal or gate current, that is defined by Ig1 and Ig2. That means the gate pulse across Ig1 for, that is T1, and Ig2 for T2. Actually, this is actually always try to maintain this pair, suppose T1, T2 and T3, T4 at the same instant. That means we should apply the gate pulse at the same duration. Okay, that is why Ig1 and Ig2 both can be replaced by a single axis. Okay. Next is, that is Ig3 and Ig4. That is why next one is Ig3 and Ig4. Okay. And this is actually V0, or the output voltage across the load, and this one is the I0, is the output current across through the load, and this one is the voltage appeared across the thyristor T1 and T2, and the voltage appeared across the thyristor T3 and T4. The most important part in this case, that is the selection of the firing angle. Actually, as we are using the RLE load, and which is E defined by the back EMF, That is why the polarity of this particular E, that is opposite of the supply voltage. That means when the supply voltage goes positive, then the polarity of the output voltage, the upper part will be positive and the lower part will be negative. And when the supply voltage is not fed to the output voltage, then the total output voltage will be leaded by the back EMF, that is defined by E. Similarly, in this particular case, still the voltage across the upper part, that should be positive, and the lower part, that should be negative. That means in the both cases, across the load, the voltage is always positive and in the same direction. That is why through which we can do the rectifier operation. But this firing angle across T1 and T2 and for T3 and T4, that should be selected properly. Okay, as it is true when the thyristor when the converter is not working, then the total voltage is leaded by this E. Okay, that means we can define both the waveforms in a same direction. As E is in the same direction with respect to positive supply, that is why we can draw this part E is a straight line. As it is a DC, we can consider the back EMF in terms of DC, that is why in a straight line. Okay, so think about this particular point where this E, the waveform is E, waveform of E, and the waveform of the positive half cycle of the supply, that will coincide in this particular point. That means at this particular point, up to this particular point, we cannot apply the triggering pulse, okay, across the thyristor. Because what? Because if we consider, see, this point is suppose theta 1, that means 0 to theta 1, what happened? In this duration, the positive, due to application of the forward half cycle, the supply voltage goes positive from its low value to a particular value, means from 0 to theta 1. But before theta 1, 0 to theta 1, all the cases across E, it will provide the constant magnitude. This is the E magnitude of the E. Okay, that means we cannot fire the SCR T1 and T2 before the theta. As because if we are trying to fire before theta, that means what? Then E has the higher magnitude with respect to supply voltage. That means as because E is high in magnitude, that is why upper part, this will be positive and this will be negative. Then current try to flow this direction or this direction. As the supply voltage is low magnitude with respect to E, that means all the cases, all thyristors are in reverse biasing condition. We cannot fire any one from the given 8 number of thyristors. That is why the selection of the firing angle, that should be considered by using this theta, that will be equal to what? That will be equal to Vm sin the expression, that should be equal to Vm, that is Vm sin theta 1, that should be equal to what? That should be equal to E. That means we can write theta 1, that should be equal to sin inverse E by Vm, that is E by Vm. That means this is the minimum angle up to which we cannot fire, but we can apply the triggering pulse above theta 1. Oh, okay. This is the starting point of applying triggering pulse. Similarly, we can consider the next thing also. Okay. If we consider this is suppose the point of theta 2, so we cannot apply theta 2, so we cannot apply the triggering pulse above theta 2. The similar case will be happen as the thyristor will be in reverse biasing condition, due to the E has the higher voltage with respect to the supply voltage. That is why we always try to maintain the firing angle in between the range, that is alpha, that is theta 1 to theta 2. Okay, this is the selection of the firing angle. So when the supply voltage goes positive, as well as we are applying the triggering pulse across T1 and T2 with an angle alpha which is greater than the previous discussion theta 1, then the T1 and T2 becomes on. And then the current starts flowing from supply to T1, then the load, and coming back to T2 and to the supply. In this way, the current is flowing from upward to downward direction across the load, and voltage appear across the load. The upper part is positive and the lower part is negative. Okay, fine. So that can be happen in case of the positive half cycle of the supply voltage. Suppose after pi, the supply voltage goes negative. So after pi, the supply voltage goes negative. That means in case of the secondary winding of the transformer, it will be positive, it will be negative. That means then the current starts flowing from this direction to T3. That means T3 and T4 will be forward biasing condition, as well as we have applied the triggering pulse across the T3 and T4, that is pi plus alpha in this case. Okay, that is pi plus alpha. Then once the thyristor T1 and T3 will be fired or it becomes on, then automatically the current starts flowing to the thyristor T3 to the load and coming back from T3, T4 and to the load. Again, in this case, the voltage appear across the load, that is upper part is positive and lower part is negative, as well as the current starts flowing from upward to downward direction. That is why both cases, when T1 and T2 has fired as well as T3 and T4 has fired, then the voltage appeared across the load that remaining in the same direction. That is why we have drawn all the output voltage in the same direction, as it will give us the pulsating DC or DC output. That is actually the concept of rectification operation. Now see what, when T1 and T2 has fired, then immediately the supply voltage will be appeared across load. That is why duration, in this particular duration where Ig1 and Ig2 has given from alpha to pi, that is the supply voltage that will be appeared across the load. This is the load voltage. Oh, okay. Up to which point? Up to this point. As 0 to pi, as the inductor is there, that is why inductor starts storing energy inside it. Then the current flowing across the inductor in this direction. Once the inductor get fully charged with respect to the supply value Vs, then it try to discharge. That is why once the supply voltage goes negative, just cross the point of alpha, then inductor starts discharging. And the discharging current starts flowing in this direction, due to which the thyristor T1 and T2 again is in, for again thyristor T1 and T2 again still under working state, because it is true during the negative half cycle of the supply voltage, thyristor T1 and T2 can be reverse biased, but the holding current is not fall to, but the anode current is not fall below holding current, as the discharging current is high enough to maintain the conduction of thyristor T1 and T2. That is why it can be discharged up to the point of this one. That is why there is a question for the negative peak. So once we are giving the next triggering pulse to the next pair of thyristors, that is T3 and T4, then again it will be started in this way. So in this way the total scenario can be happen, and we can experience the total output voltage waveform in this way. Okay, that is why due to presence of inductor during this duration, the current gradually increases up to this point alpha. Pi. When the supply voltage goes negative, then the inductor current try to discharge. That is why the inductor current falls from its maximum value to initial value. In this way, it will be repeated for the next cycle onward. So this is the waveform of the voltage, and this is the waveform of the current. Okay. Now the terminal voltage across the individual SCRs. So when T1 and T2 has fired, then no voltage is appearing T1, T2. Then the total voltage will be appeared across T3 and T4. That is why when T1 and T2 has fired, in this particular duration from alpha to pi plus alpha, no voltage is appearing across T1 and T2. Total voltage is appeared across T3 and T4, and it will follow the same waveform and which is taken out from the supply voltage. Similarly, when T3 and T4 has fired in this particular position, that is suppose from pi plus alpha to pi plus alpha, then in this particular region, then the total voltage is appeared across T1 and T2, that is defined by this waveform, and no voltage is appeared across it is in on state, that is why it is behaving like a short circuit. So this is all about for the waveforms, and which can be demonstrated individually from the circuit diagram. In addition, as we are using the inductive load, that is why it should cover the two-mode operation. Okay, that is, it can cover two-mode operation. That is, when the inductor starts storing energy, then the supply voltage, that is positive, as well as the current which is flowing to the inductor, as we assume that is a positive current, that is the inductor, the current is also positive, and which will actually cover the first quadrant operation, and that can be happen in case of charging time of inductor. Once the inductor is fully charged, then it try to discharge, as well as at the particular duration the supply voltage goes negative, that is why supply voltage goes negative. But inductor charging path and inductor discharging path both are remaining in the same direction, that is why it starts discharging at the same direction of the charging current, that is why for the both purpose it will cover the positive current. That is why in this case the supply voltage is negative but the inductor current is positive, that means the power is negative. So that is why it can cover the fourth quadrant operation. That is why for the first quadrant operation, the total power is delivered from supply to load, that is called rectification operation, and in case of the fourth quadrant operation, actually the power is delivered from load to supply, this is called inverting mode of operation. Now we are going to derive the expression of average output voltage current and RMS output voltage current. As the output voltage is pulsating DC, that is why we should calculate the expression, we should define the expression of the average output voltage and RMS output voltage. So to calculate the average output voltage, this is the expression, that is VDC, that should be equal to 2 by 2 pi integration of alpha to pi plus alpha Vm sin omega t. As we know, to form the expression of the average value, we should take care of the number of peak in the forward direction divided by the total cycle and integration of confined region that has started from alpha to pi plus alpha in this waveform C, in where the output voltage, that is defined by this one, it has started from alpha and to pi plus alpha. That means this peak is confined between two limits, that is alpha to pi plus alpha, as well as in a complete cycle, that is 0 to 180 degree, the number of forward peaks, that is 2. That is why we can derive the expression in this way, that is VDC equal to 2 by 2 pi integration of alpha to pi plus alpha voltage expression, instantaneous voltage expression, that is Vm sin omega t d omega t. So after integrating this part, we can have, that is Vm by pi, okay, that is Vm by pi sin omega t integrating part, that is minus cos omega t, and lower limit alpha, upper limit pi plus alpha. And considering this upper and lower limit, that is Vm by pi, that is minus cos pi plus alpha plus cos alpha. And after simplification, we will have, that is Vm by pi, that is plus cos alpha, that will give us, that is 2 cos alpha. So the expression will be 2 Vm by pi cos alpha, right? So the average output current that can be replaced by, that is IDC, that should be equal to VDC minus E by R, not VDC by R. Keep it in your mind, as it is a RLE load. That is why always the E should be in opposite direction with respect to supply voltage. That is why the expression that can be written as VDC minus E, that is a voltage expression, divided by R. Now, to calculate the RMS voltage, we have taken the same expression and which we had formed in case of the formation of the average output voltage. That is 2 by 2 pi integration of alpha to pi plus alpha Vm square sin square omega t d omega t under root. As the RMS value, that means root square term. That is why after simplification we can have, that is 2 Vm by 2 pi into 2 Vm square by 2 pi into 1 by 2 integration of alpha to pi by 2 sin square omega t. So it is divided by the 2 and multiplied by the 2 to form the expression in terms of 1 minus cos 2 omega t. That is why we can rewrite the expression like Vm square by 2 pi integration of alpha to pi plus alpha 1 minus cos 2 omega t d omega t. Now we can integrating the part and we will get the result, the constant of integration, that is omega t, and cos 2 omega t, that is 1 by 2 sin 2 omega t, and considering all the lower limit and upper limit. That means we can simplify the equation, that is Vm square by 2 pi omega t alpha to pi plus alpha minus 1 by 2 sin 2 omega t alpha to pi plus alpha. So now considering the value, that is alpha, that means pi plus alpha upper limit minus lower limit, the similar can be done in this case, that means sin 2 pi plus 2 alpha minus 2 alpha, then we will get the expression this one, and considering or calculating the limit value, so we can simplify the expression, that is Vm square by 2 pi minus 1 by 2 sin 2 sin 2 alpha minus 2 alpha, that will give us 0. So ultimately the expression can be written as Vm square by 2 pi into pi under root, and pi both will be cancelled. So finally we can have the result, that is Vm by root 2, which is actually Vs. So this is the RMS value of the converter circuit. Okay. In this way we can calculate the RMS current also, that should be equal to what? That should be equal to Vrms by R, not Z, as for average value calculation. So di dt, that give you 0. That is why IRMS, that should be equal to Vrms by or Vs by R. So this is all about for the single phase full wave control rectifier with RLE load. Okay. So thank you for investing your time. So thanks a lot.